Let me begin with a word of prayer. Heavenly Father, we thank you again for your many blessings to us. I thank you for these students. Just ask you'd guide our steps today again, Lord. And we thank you for the nice weather outside and for your creation and for being the good and awesome God that you are, Lord. In your name I pray. Amen. Okay, so today we're talking about parabolas. Any questions before I dive into that, though? Okay. So I want to try to describe how we can understand how to graph a parabola and how to properly characterize it, right? And so I think I'm going to resist the urge to give you the general theory at the start. I'm going to work a couple of examples, then we'll get the general theorem, okay? But I will just say this much. Generically speaking, if we have y equals to ax squared plus bx plus c, all right, where a is not equal to 0, right? And b and c, a, b, c are real numbers, right? If you have that context, all right? So a, b, c are what? They're called the coefficients of the parabola, right? If this is the case, if you're looking at such a graph, well, you've got a parabola, right? It either opens up or opens down. And of course, we'd like to characterize it, right? So some things that we're going to be looking for, like we're going to look for the vertex. We want to find the X-intercepts, the Y-intercept, these sorts of things, okay? So let's look at example 1. Suppose you've got, f of x equal to, x squared minus 4x plus 5, all right? So I want to understand what's the graph. I want to graph y equals f of x in this case. All right? So in this case, I think the right thing to do is to complete the square. All right? So here we have y equals x squared minus 4x plus 5. If I complete the square on that, what happens? I get what? I get x minus 2 quantity squared minus 4 plus 5, right? And so that's x minus 2 quantity squared plus 1. So there you go. I mean, we've completed the square. And I can use this, all right? This tells me things. Like I can look at this and I can see from this, looking at this, I see vertex is at 2, 1. The reason I see that, if you think about the formula, right? Think about the formula. What's the smallest y that can be? The smallest y could be is when that x minus 2 thing is 0, right? So you get 0 squared plus 1. So 1 is the smallest y could be for this formula. So that must be what's the vertex of the parabola, right? So basically, you got 2, 1. So 2, 1 is the vertex, right? So that's 1 point on the parabola. See, because if you plug x equals to 2 into the formula, you get 1 out, right? I think we can agree with that. What other point do you know on this parabola? Without any kind of further much work. Look at this, right? Right here, 5, right? This tells me the y-intercept. Right? F of 0 is equal to 5. So the y-intercept is 5. The constant in the parabola will give me the y-intercept. So in this case, that's up here. Right? And then the way it works is the parabola is always going to be symmetric about its vertex. So if I can just kind of mirror that like this, there you go. That's the graph of this parabola. There you go. That's the graph of y equals x squared plus 4, rather minus 4x plus 5. Okay? Let's look at another example. Let's look at y equals to x squared minus 4x plus 5. I mean, I just did that, didn't I? Minus 5. There we go. Very similar, yet very, very different. What's the right approach here? Now, I could complete the square. In fact, let me do that, right? Let me complete the square again. We could all use practice on that, couldn't we? So this is x minus 2 quantity squared what? I have to subtract the square of 2, right? So I have to subtract 4. And I still got the 5. So what do we got? X minus 2 quantity squared. In this case, minus 9. Completing the square. So I take half of 4, half of minus 4, which is minus 2, and then I have to subtract the square of minus 2 over here. So the square of minus 2 is just 4.
Okay.
Yeah. But the answer to your question is I completed the square. So that's what that step is. Now, once I get to here, I can tell you where the vertex is. All right? This, I can see vertex at, in this case, 2, comma, minus 9. Just from looking at that formula, that shows me the vertex is at 2, comma, minus 9. See, because the smallest the formula can be is minus 9. That happens when x equals minus 2. Excuse me, when x equals 2. When x equals 2, that x minus 2 term is 0. Right? That's the smallest that formula can be, which means it's the vertex of the parabola here. What else can you do for this one, though? You're like, you and you're completing the square. I know easier things. What are the easier things we could do here? How about just from the, yeah?
Could you like factor it out?
Yeah, we could factor it down here, right? X minus 2 plus 3, x minus 2 minus 3. You could do like that, or you could have just done that straight up here, right? X plus 1, x minus 5, right? So you either can see that from, as I call it, the algorithm, right? Completing the square, difference of squares. Or you could just straight factor it, right? If you see it. So what's the deal then? What does that mean? What does it mean? Y equals x plus 1 times x minus 5. What does this tell me? This tells me X-intercepts for my graph, right? Of minus 1, 0 and 5, 0, right? Those are 2 points where the graph of the parabola crosses the x-axis, right? And so, let me draw it, if I can. Let's see, I need minus 9. And let's see here, I need 1, 2, 3, 4, 5, 1. Right, so it's got x-intercepts of 5, right, 0, over here, right? And also minus 1, 0, which is like here. What's the where's the y-intercept? What's the y-intercept? So that's always f of 0 right here. So if I'm always calling the thing f of x, okay? Just for the sake of common language, minus 5. We're graphing y equals f of x. Here f of x is equal to x squared minus 4x minus 5. All right. So minus 5 is the y-intercept. That's like 1, 2, 3, 4. So here-ish in my current picture. And where is the vertex? 2 comma minus 9, right? So about right here. 2 comma minus 9 vertex. So what's the graph look like? It looks something like that. Can you tell me what's the axis of symmetry? What's the axis of symmetry for the parabola? Do you guys know that? So the axis of symmetry cuts it in half, right? So the axis of symmetry is just a vertical line that goes through the vertex. So like the axis of symmetry for this one is just x equals 2. See that? I can reflect the graph across that vertical line right here. X equals 2. So-called axis of symmetry. So if you know half of the parabola and you know the axis of symmetry, you can create the other half by just reflecting it over the axis, yeah? That's essentially how I graphed this last one. See, because I know about the axis of symmetry, so I knew that by having the y-intercept of 5 here, I knew I could just mirror that on the other side of the vertex. That's actually how I made this picture over here, truth be told. Even though I only know 2 points, I just knew the y-intercept and the vertex. That was enough for me to graph it. If you know the vertex and you know one other point, you can graph the parabola. Yep.
If you didn't complete the square in example 2, and you just factored from the beginning,
right.
find the vertex.
Ah, great question. So how do we find the vertex if we don't complete the square? Right. So where is the vertex? So let's go through a derivation. Did you pan over? Yes. Okay, cool, thanks. Let's go through a derivation here in general, yeah? So suppose we start with y equals to ax squared plus bx plus c, right? So let's figure out where the vertex is on this thing. So what we're going to do, factor out a. So I get x plus x squared plus b over a, x plus c over a, yeah? Then I'll complete the square. So it's going to take me a few minutes to answer your question, how do you find it without completing the square? But I'm going to give you an answer to that question, okay? So I have not forgotten about it. I'm just taking my sweet time to answer your question. So plus c over a. So I completed the square by dividing by the coefficient of the x by 2, b over 2a into the b over a. You square that, you have to subtract the square of this thing like so. And then I'm just going to rewrite this ever so slightly. X plus b over 2a quantity squared plus c minus b squared over 4a. Notice the a is only multiplying the squared term now, all right? So we can compare this versus y equals to a times x minus h quantity squared plus k. So this is the so-called vertex form of parabola. So if you can put the equation of the parabola in vertex form, it manifests where the vertex is. It makes it clear. It's just in your face. It's right there. This has vertex h comma k, if this is the pattern. Okay? So the usual notation is h comma k for the vertex, okay? That's just standard notation, yeah? So like for example 1, h was equal to 2, k was equal to 1 for example 1, okay? For example 1, h was equal to 2, k was equal to 1. For example 2, h was equal to 2, k was equal to minus 9. And I was using this vertex form of the parabola idea to identify the vertex. That's what remember I said see the vertex? Both of those times I was using pattern matching with the formula we had against this generic form of the vertex, right? Okay, so great. Now make the same thought relative to the arbitrary parabola and the vertex form, what do you see? What's the formula for h? What's the formula for k in terms of the coefficients? See, we have a theorem here. Theorem. H equals to, look at this, compare. Minus b over 2a. K equals to what? See, compare these two. C minus b squared over 4a, right? So if you want to find the vertex without completing the square, you could use these formulas. I don't recommend it, really. I think it's easier to complete the square than to try to implement these formulas, usually. I mean, it's a lot to remember. Now, you guys have an advantage over me in that you have a formula sheet for your test, so I guess you could use the formulas reasonably, right? Do these formulas work? You want to try them out? Take them for a spin? Yep. Yeah, you get a formula sheet. I gave you a formula sheet on test 1, right? Ah, you didn't know. Ah. That is unfortunate. I did say it, right? Yeah. Okay, okay. Yes, front and back. You can, put a picture of your beloved Psalms, Proverbs, Ecclesiastes, whatever floats your boat. Quotes from Chuck Norris, whatever. So let me just show you, if you don't believe it. So example 2, we had what? We had y equals to x squared minus 4x minus 5, right? So here a equals 1, b equals minus 4, c equals to minus 5, right? So if you use the formulas, the handy-dandy formulas there, this gives you what? H equals to minus b over 2a, which in this case is? Example 2 revisited.
Oh, okay.
Continued.
Sorry.
No, you're fine. Good question. 2 times 1. So we get what? 4 over 2, also known as 2. K, what was K? C minus b squared over 4a. Now, if you asked me what the formula was for the vertex on any given day, I don't know these formulas. I don't have these memorized. I do nothing but math. I don't have these formulas memorized, right? Because I can complete the square, It's just easier. C, where is C? Oh, here. Minus 5 minus what? Minus 4 squared divided by 4 times 1, which is what? Minus 5 minus a minus 4, which is minus 9. So does that answers your question, yeah?
Yes, thank you.
Are there any other hidden facts I should share with you guys about parabola? There's so many things to say about a parabola, right? So for example, one of the things we could already say today is in example 1, our polynomial was prime, right? And a prime polynomial has what? Has no x-intercepts. See that? Whereas in example 2, this was not prime, right? And there are x-intercepts. Yeah? Let's look at example 3 here. Suppose we have y equals to minus 2x squared minus 4x minus 2. All right, I'm gonna complete the square again. Minus 2. That's x squared minus plus 2x plus 1. So I factor out a minus 2. Yeah? And, well, maybe I don't need to complete. I mean, completing the square and factoring are the same thing here. Can you guys factor that? What is it? Right? So in this problem, the problem of finding the vertex and the problem of finding x-intercepts, it coincides. It's the same problem. See, like, if you compare this, right, now, what you got to do to find the vertex, compare this and this, yeah? See it? look at it. What do you see? You see h equals to minus 1, right? K equals to what? It's like wings on an elephant, right? You know, they're set to 0, right? So, I mean, plus 0, yeah? So the vertex here is at minus 1 comma 0. What else is minus 1 comma 0? It is an X-intercept, yeah? So the vertex and X-intercept here, they're at minus 1, 0. And so if I graph this thing, what happens? How do I set the scale? How do I set the scale? What other easy point can you give me on this parabola? 0, negative 2. Very good. So that's called the y-intercept, right? So look here. This tells me the coefficient, the constant term, right? That tells me where it hits the y-axis, which is about right here, right? That's the vertex. That's a point on the graph, right? Remember, I have my axis of symmetry, like that. And so I can just kind of, I can try anyway. Why? Well, anyway, I don't draw well down here. I tried anyway. So it looks something like this, right? Notice that the leading coefficient is negative, which means it's one of those parabolas which opens down. Yep. Go for it. For the vertex?
Yeah.
I looked at it. I pattern matched. I compared this right here, which you got to use your imagination, right? There's a plus 0 here, yeah? So look at this and look at that. What is the pattern? The pattern is that you've got minus a minus 1 here, which makes h equal minus 1, plus 0, that makes k equal to 0. It's the same thing I'm doing when I'm telling you a is equal to 1, b is equal to minus 4, c is equal to minus 5, right? I'm matching this expression with the generic form to identify what a, b, and c are. Same idea. Yeah.
So the reason why the vertex and the x-intercept are the same is because they're the same of factoring the squares, the same as just regular factoring this one, right? Is that why they're both?
Yeah, they're both the same. When we have a repeated root, when we have a repeated root, the vertex is going to be on the x-axis.
Okay.
And I like to, in this case, I like to say that the parabola bounces off the x-axis, just as a way of kind of picturing it. See, it bounces. Boop, like that. And I'll continue to use that bouncing language as we look at more interesting polynomials going forward, yeah? Question? Well, I don't have enough yet here. Let's do another example. Example 4. Suppose you got y equals to x squared minus 8x, all right, plus 1. I want to graph this thing. All right. So here, I'm going to complete the square again. So I've got x minus 4 quantity squared, yeah? And then I have to subtract 16. I add 1, right? So what goes on here? We get x minus 4 squared minus, well, you could think of that as the square root of 15 squared, yeah? Well, fine. My bad. Let me take a breath here. Okay, stop right there. Stop right there. Now we can see what the vertex is. Where is the vertex? Four minus 15. So I was talking to Dr. Putney and earlier this semester, and he's like, the main thing he sells his students on, the reason they need to complete the square is so they can find the vertex of the parabola. I think it's a decently I mean, that's not wrong, but I see so much more virtue in it than just that. Because it allows us to factor this as well, right? Because going a step further, now I can look at this as x minus 4 squared minus the square root of 15 squared, yeah? Which is, by the difference of squares idea, x minus 4 plus root 15, x minus 4 minus root 15. Why do we want to factor? We want to factor the parabola because that helps us see where the x-intercepts are, right? X-intercepts are interesting for graphing, right? That's where they're zero, where the graph is 0. So this tells me x-intercepts where? We've got 4, goodness gracious here, 4 minus the square root of 15, comma 0, and 4 plus the square root of 15, comma 0. Those two values, when you plug them into the factors right above, make the factor 0, right? Now, I mean, oh man, I think I left my calculator at home. That was a bad move today. So roughly speaking, the square root of 15 is really close to the square root of 16, right? What's the square root of 16? 4, right? So square root of 15 is, you know, maybe 3.8-ish, give or take. So with that, I can make a pretty good sketch of the graph, right? What's going on here? We need things going from, so basically this is approximately like 0.20, and this is approximately 7.80, yeah? That's roughly speaking where the x-intercepts are. And what else is going on here? Our vertex is at minus 15, so I guess I probably should make myself have a lot of real estate below the x-axis in my graph, yeah? So I've got x-intercepts at like 0.2-ish, like here-ish, and let's see here, I say 15, so I'll say that, let's say that that's 8. So almost 8. So this is about minus 8 is here, and about, okay, so where's my vertex? My vertex was at 4, right in between these, yeah? Just 4 minus 15, so it's, the vertex is right here-ish, right? And so where's one other point we can get for free almost is what? What's the y-intercept for this? 0, 1, right? So y-intercept's up here. Although if I had some graph paper, it'd be better, of course. So something like that. There you go. So how else could we find the x-intercepts? How do you find the x-intercepts? Do you guys remember? How do you solve ax squared plus bx plus c equal to 0? Many of you insisted on, I asked you to factor, and yet you insisted on solving the equation, right? Yeah, the quadratic formula, right? So of course, we could add to our repertoire here that the x-intercepts are where? Theorem, ax squared plus bx plus c equals to 0 has x-intercepts at x equals 2 minus b plus or minus the square root of b squared minus 4ac, all divided by 2a, provided what? what do we need? We need that b squared minus 4ac is what? It must be greater than or equal to 0. Otherwise what? Otherwise the solutions are complex, which means that there are no x-intercepts. Like in example 1. So this thing is called the discriminant. If the discriminant is negative, that means your polynomial is, your quadratic is prime, so there are no x-intercepts. But otherwise, the x-intercepts you can also get from the quadratic formula, although I do not advise it. I think completing the square and factoring are way, way smarter ways to do it. Did you get over there? Okay.
Yeah.
It's thank you. So let's see here. What happens if you add the solutions to the quadratic equation? Do you guys notice? Check this out. So let's try add solutions to ax squared plus bx plus c equals to 0. What happens? You've got minus b over 2a, right? Plus the square root of b squared minus 4ac over 2a, right? That's the plus solution. Take that and add it to the other one. What happens? See what happens when we add the solutions? Let me call these solutions R1 and R2. Okay, so what's root 1 plus root 2? Is this, right? So root 1 plus root 2 is what? Do you guys see what cancel? You should see something canceling, right? The ugly part cancels, right? The square root part. See it? It's the same thing with a plus, but with a minus. These cancel. And you're just left with minus b over 2a minus b over 2a, which is what? Negative just b over a, right? Because if you add a half plus a half, you get a half plus half is 1, right? So what's this mean? This means that if we take R1 plus R2 and divide by 2, we get minus b over 2a. What is minus b over 2a, though? What did we discover earlier today? Right, it's the vertex, right? So this is h. So this is another theorem that we have for the parabola, which relates what? This says that the average of the roots is where the vertex is. So the vertex is at the average of the roots. So here, R1 and R2 are called roots. Yeah? You know what's interesting? One of the things that was surprising to me about this is this is still true when the roots are complex. It's still true when the roots are complex. Even though I can't picture them, you know, it's still true. So let me show you that, yeah? So here's one. Example 5, I suppose. So let's look at y equals to minus 2x squared plus 6x. All right. Minus maybe, I think if I do minus 10, that'll do it. Reserve the right to make that number bigger or smaller on the end, okay? So here we go. We factor out the minus 2. We've got x plus 3x, x squared rather, plus 3x minus, plus 5, right? Oh man, this one's going to have fractions. I guess that's good for us. We should deal with fractions from time to time, right? Excuse me. So I have to complete the square. This time I get what? X plus, yep. Oh.
Wouldn't that be a negative 3 instead of a positive 3? Because if you
Oh yes, thank you, thank you. Very good, very good. Minus 3x. Excellent, thank you. Good call. So minus 3x, so that's going to give us what? X minus 3 halves, right? Okay. Now, completing the square, right? So I have to subtract 9/4. That's the square of 3 halves, and I still have got my plus 5 there. But how many fourths is 5? 5 is 20/4, right? So I get 20/4 minus 9, so I get 11. Plus 11/4, yeah? Now be careful, that's not vertex form. You see how vertex form works? Vertex form has the a factored out just from the first term, not from both terms, right? So to get the vertex form, I have to do one more step, yeah? I have to multiply the minus 2 through there, right? And so this gives me minus 2 times x minus 3 halves squared minus 11 over 2. So what's the vertex here? Vertex is 3 halves and minus 11 halves. All right, now one of the things we haven't done much until now, this might be the first time I've done it in here, but I'll do it, is I can factor using complex numbers. So this I can look at as x minus 3 halves squared minus the square root of 11 over 2I quantity squared. See, if you take the square root of 11 over 2 and you square it, you get back 11/4, right? If you square I squared is minus 1. So this is a sneaky way. It's a sneaky way of writing a positive term as a negative term squared. All right? And if I do that, then I can use difference of squares with complex numbers. And here it is. So I get x minus 3 halves plus the square root of 11 over 2 times I, x minus 3 halves minus the square root of 11 over 2 times I. So this is a prime polynomial in the sense that we cannot factor this over the reals, right? What are the zeros? So from this, you can read it off, right? Zeros, x equals to, 3 plus or minus I times the square root of 11 over 2 are the, our roots of, my minus 2x squared plus 6x minus 10 equals to 0, okay? The complex solutions. Do you see what happens? Look what happens when you add these two together. See what happens? When you add these two together, you get 3 halves plus 3 halves, and the I root 11 over 2 and the minus I root 11 over 2 cancel. And again, you get the average of these is exactly 3 halves as it happens. Anyway, let me get to the point here. What's it look like? The vertex is at 3 halves minus 11 halves, right? So that's 1.5 let's see here. So it's got a y-intercept of -10, yeah? And it's got the vertex at 1, let's say this is 1, 2. All right, so it's not quite to scale, yeah? So at 1.5 rather, minus 5.5, which is about here on my picture. That's your vertex, right? And what's it do? It's opening down, right? So the picture is something like, so here's the graph. That vertex again is 3/2 minus 11/2. So, you know, this is a kind of ugly example, but we should work an ugly example from time to time. Some of your homework is ugly, right? So all of my examples shouldn't always be integers. I try to make most of the examples integers so that there's less trouble to understand it as I'm talking about it for you guys. But, you know, the homework should have fractions in it because you do need to work in fractions, of course. Okay, so I have shown you a couple different forms of the parabola today, right? We have talked about what? We've talked about this. So we started with the standard form of the parabola, right? We talked about the vertex form of the parabola, right? But there's another form I should probably write out. Let me just put them all in one place, yeah? So we can have standard form, which is just y equals ax squared plus bx plus c, right? We've got our vertex form, which is something like y equals a times x minus h squared plus k, right? So vertex form is nice because it shows you manifestly where the vertex is, right? But there's another form, right, which is a factored form. Y equals to a times x minus r1 times x minus r2, right? This shows us what? This tells us immediately that like 0 r1, other way around, sorry. This shows us that 0, I just did it again, r1, 0, and r2, 0 are what? Are X-intercepts, right? If you have it factored, then you can read the X-intercepts right off of it, right? So these are all important. I think in terms of graphing, of course, the vertex form and the factored form are very helpful. How would you graph the standard form? Like, you'd go back to the thing we did, like the class before last, I think it was, when I just spent 15 minutes with a table of values going ka-chunk, 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 right? Like, that's kind of how I would do that. But, so, example, what am I on? Example 6? Suppose you have y equals to 3 times x minus 2 times x plus 10, right? And then I ask the question, where's the vertex? How would you do it? How would you figure that out? Here's how I do it. I would say r1 equals to 2, r2 equals to minus 10, right? It has roots at 2 and minus 10. So r1 plus r2 over 2 is 2 minus 10 over 2, which is minus 8 over 2, which is minus 4. So the vertex is at 4. What is the vertex, though? Vertex is at h equals to minus 4. What is the vertex? Well, if we think of this as a function, right? Think of this as f of x. Then k is always going to be f of h, which would be f of 4. What is f of 4? F of 4 here is 3 times 4 minus 2 times 4 plus 10. See that? So this would be 3 times 2, 6 times 14, whatever that is.
Or negative.
What?
Or when you're putting in.
Oh, did I have a negative 4? Oh, my bad. So minus 4, thank you. That makes it a little bit different. So that gives me 3 times minus 6, which is minus 18 times 6, right? Which is, I think, 60 plus 48, which is minus 108. So there you go. Vertex is at where? Minus 4, comma, minus 108. Now, what's another way you could have done this problem? You could have done what? You could have multiplied that out, figured out what A, B, and C are, right? And then you could have used the formula we derived for K over here. You could have done that. That's another way you could have done this problem. Figure out the A, B, C, fall back on the theorem. Anyway, I hope I've given you some toys to play with. Have a good weekend.